Hi, everyone. Today we looked at an example of regression analysis using house prices in King County. And I wanted to go over the solution to those exercises. So just a little bit of background here. We have an opportunity to predict the price of a home based on a collection of specific characteristics that describe that home. And one of our goals is to identify the most important features in this data set and then build a predictive model using linear regression analysis. One of the things we went over today in class was some of the assumptions, the principles, and methods surrounding linear regression analysis. And for those who are doing a project involving linear regression, you may want to review those concepts and make sure to look at the Boston housing example for your sample case for the project. For everyone else, it's pretty important to understand how to work with numerical data when making predictions. So these classwork exercises go over some of the key steps that would be needed early in a regression analysis project, linear regression. Okay, so here we have our data. We have some information about these homes, and we have some more detailed information about these variables. As always, we start by importing our data, or importing our libraries, I should say. So we run that step. Some of the key tools to notice are these. So we have stats models, which is you're going to import the ordinary least squares. So that's OLS, ordinary least squares. That's a typical tool used for building a regression model. Least squares regression minimizes the square differences between the actual values and the predictive values. So then we have stats models here. Then we have the linear regression from sklearn, and some of the usual tools as well. Now, one of the things we went over a couple of times in class, and you'll see it in those videos, was how to import data in a Colab notebook. So I share that data file in our Teams workspace, and all you would have to do is download it from here. Could download it here, download, and then that would be in your files, and you can drag that file over into your Google Drive. So we can just go over that right now. Upload, file upload, and then there's our data. So we would open that, upload that, which I've already done. And then when we want to get the link, we would right click on the file, click get link, copy that link, and then that is what goes into this space under original URL. So you would paste that into the dashes that you have in your notebook. I wanted us to have a chance to practice that step so that you're not stuck on this at some point in the future when you're doing your own data analysis projects. Okay, so here's our data frame. We can see the variables. It's a good idea to get some information about the data. One of the things we want to take a look at is the data types and check for missing values. It looks like we have 21,613 observations for each of the variables, so no missing values. But we can see that we do have some data types that are objects, just one, it looks like. So we'll need to consider whether that needs to be omitted entirely or if it needs to be converted into something numerical that we can use as part of the model construction. So that is the date, and we may not need that, right? So the date is not going to be informative in our predictions. So we would then drop that from the data frame. So we can do that by, say, creating a new data frame, df, and then setting that equal to df where that variable is dropped. X is equals 1 means we drop the column, the full column. Okay, then we're going to do some data descriptions. We're going to create a summary variable called summary, reference the data frame that we created, use the describe method, and then transpose just makes this more readable because we have so many columns. It makes sense to look at the columns down the page and the statistical metrics across the page, just more readable there. Okay, moving along, I'm going to do some univariate analysis. So here we're doing a for loop, which we see in a lot of cases is a form of program control. So for I in the data frame dot columns, this is one way to access the columns. We are going to create histograms where each explanatory variable is going to be one of the columns. Okay, so notice that the iterative variable is going to be our x variable in each case. So that basically changes which variable is going to be in the histogram. So we have ID, that's not going to be a really useful variable. We have price, bedrooms, and so on. So that I, right, the I represents each of the columns in the data frame. Some of these are more informative than others, right? Some of them actually have a continuous distribution, square feet above, square feet in the basement, year built. Kind of silly to see that as a histogram. Makes more sense to look at it as a time series. Year renovated, zip code, not really a continuous variable, so that's not meaningful either. Latitude, longitude, square feet of living space, pretty useful variable, and so on. All right. So we may have some observations here. Notice that the target variable is slightly skewed. In these cases, it's a good idea to apply a log transformation. And that helps us to avoid contradicting the assumption of linearity, which is a condition for applying a linear regression model. Usually just transforming the target variable or our y variable helps us take care of this assumption. Sometimes it's necessary to transform the predictor variables as well. But maybe I would say go back to that if you have a real problem with model performance, that is, you see a real difference between the training data and the testing data results. So we create a new variable. We can set a new variable called price log and set that equal to the log of the price. We can re-examine the histogram to see that we do get a better symmetry. Okay, so more symmetric predicted variable, I should say target variable, that's more symmetric, then we can rely on slightly more linear patterns between the predictor variables and the target variable. Okay, so some observations to make here. Next, we take a look at a correlation matrix with a heat map. And remember, we are looking for variables that have a correlation greater than 70. If it's exactly 70 or 0.7, it's kind of your call to decide whether or not that variable should be removed. Okay, so we can see some cases where there are correlations. We're mostly looking for correlations between the predictor variables. So for example, square feet of living space and then square feet of living space 15. Those are highly correlated. Square feet above, square feet of living space, naturally, those are correlated. So we want to only be inputting independent information into the model that is kind of mathematical concept behind the scenes of a linear regression model. It has to do with orthogonal vectors. If you ever look at this more mathematically, so that needs to be taken care of. So we really want to take a close look at this. So we then look at the scatter plots to visualize the relationships in more detail, and this can be done using the scatter plot function from Seaborn. SNS stands for the Seaborn library. So we can look at these. So scatter plots, taking a look at these patterns to see if those correlations are coming from actual patterns or from outliers. Okay. So in those cases where the correlation is due to outliers, we can remove the extreme values. So we could set a new data frame transformed equal to the data frame where the square footage of the lot is less than 125,000, and something similar for the square foot of the lot 15. I think that's the 2015. And we can look at the correlations from there. All right, so in some cases, there's a correlation that is still high, and that means we cannot conclude that the strong association is due to outliers alone. Okay, so our last step in this project, in this classwork, is to separate the data. Okay, so we're separating the dependent and independent variables, or I should say the predictor variables and the target variable of interest. So the way that is usually done is we set y equal to the data frame column for price log in this case. And then we set the x variables, so that's all of our predictor variables, equal to the data frame without the target variables. Okay, so the target variables are removed, both versions of the target variable, the price and the log transformed price. So that is an overview of how to set up a data set so that it is ready for linear regression analysis. Thanks.